Hey everybody. Welcome back. How are we doing? Um, okay, it's week. Oh gosh, it's week 11. Okay. The quiz happened. Let's assume that's gone well. Exercise 9 has happened. So you have written some Spark code, and I guess we return to where we left off, which was, well, I guess just for context, like we talked about Spark. It does a lazy evaluation, or is lazy, or however you want to say that. Um, and I think maybe the best summary is this: that okay, you write some code and then you do some stuff. You have some Spark, whatever. This code doesn't so much produce the data set that's in your head when you look at this code. What it does is produce the execution plan that could produce the data set. Evaluating it is the next problem when you write to disk or whatever. So, okay, that has a bunch of implications. If you've taken like 383 and you've seen Haskell doing lazy evaluation or some similar language, I think I think this would be my summary of the concept in general. It's almost always good. It's almost weird that most programming languages have no lazy evaluation. There's some tools, things like generators in Python, the iterator trait in Rust, those kinds of things that let you do lazy evaluation at the right spot. And I think the reason is it's usually good, and when it's bad, it's bad in a way that's hard for people to see coming. Maybe that's just because they're not used to it. So it was this kind of thing is what I was talking about right at the end of the last lecture. So I have a data frame. So this hasn't been evaluated. That's totally cool. And I'm going to use it twice, right? I'm using it here and I'm using it here. Well, it seems cool, right? Like, again, there's no extra memory being used or whatever on this slide. And I guess we imagine like there's going to be some kind of like result1.write and result2.write. We're actually going to use these data frames for something. But so because of the lazy evaluation, we now have this problem of like the computation didn't happen when it needed to, sort of. So we would come to this point, and I would, again, probably replace this with result1.write.csv, whatever. What has to happen to do that is, okay, calculate all the mod 3s, calculate all the length, calculate all the whatevers, count, aggregate and count and sum, and write that to disk. And then, like, of course, pandas, or Spark or Python or whatever doesn't know what's about to happen in the next line of code. What I see is about to happen in the next line of code is calculate all the mod 3s, calculate all the lengths, do this, calculate signs, and then do something different with them. So that's bad, right? I don't want to do that because, well, if it's a small calculation, fine, but that's not what we're doing with Spark. So the sort of pattern here is something like this, where I have one data frame, and just because if you make the choice to reuse a variable name, that's not what we're talking about. Like in this code, like if I had done this or I had done this, these are exactly the same story. But this data frame didn't get used 3 times. This is a whole completely new data frame, and I made the maybe slightly sloppy choice to reuse a variable name. That doesn't matter. Here, there's no reuse of a data frame if I do that, because even though it looks like I've used the data frame named values twice, it's a different one by the time I get to this line. So like sometimes I've definitely encountered students that are a little confused about what's going on, and often doing something like this will clear it up for them. You can choose to reuse a variable name. That's not illegal. But when you do it, you have to remember, like, okay, I have this data frame name values and I have this data frame name values, and they're not the same. The reuse is something like this, where this is the same data frame that's used twice in 2 different ways. And when that happens, it gets evaluated twice, because what else can Spark do if it's going to lazy evaluate? It doesn't know what I'm going to do later. That's not how the language works. What I can't do in a big data context is keep intermediate results. And like as a Haskell programmer, say, you wouldn't usually worry about this because it's like, well, how much? You're probably not doing very much, right? You're only going to do a little bit of work. So, a couple additions, a couple multiplications or something. Yeah, just repeat it. It's fine. Well, I'm not doing, things. And I guess maybe the thing I should say is, like, in something like Python, where you do have non-lazy evaluation, or C or whatever, the intermediate results you're usually thinking of are like an integer. Okay, well, store the integer in memory. Who cares? It's fine. That's not what we're talking about in this context either. We don't want to just keep all of the part-way calculations just in case. But what we can do is keep a selected part-way calculation that we've selected. And in this context, it would be that. So I would insert that method call on the data frame, or again, depending on my style, I could do something like that. And that's saying, hey, dear Spark, when you are going to calculate this data frame, store it in memory. So it doesn't mean like calculate it right now and cache it. It means when you calculate it later, still lazy evaluating, you're going to store it in memory. Okay, I better have enough memory for that, right? I better be able to do the thing that I've asked for. But the executors are each going to store the partitions that they calculate, because I sort of have promised, or I imagine, or I kind of know what I'm doing here, and I know what I'm going to do later involves using that same intermediate result again, so I want it there when I go looking. So the change, if I insert this line, is going to be new execution plan. And what happens here that just about fits on the screen is, okay, I still see the sort of lineage in either execution plan, but this in-memory relation means and store it in memory, and this means and read it from memory. So if it's already in memory, we don't have to sort of go back this far in the execution plan. So assuming I'm sort of going to do this in order, the first time I do this to create this result, yeah, we're going to do the range and the select and whatever, store it in memory. The second time, we're only going to go back sort of that far in the execution plan. We're not actually going to calculate it. We're just going to find it. If there happens to have been some problem, like we ran out of memory or an executor failed or whatever, it's still possible to go back and calculate it, but we hope we don't have to. There is a tab in the Spark web interface for that, where you can go and have a look. So, this calculation I caught about a third of the way done. 2 out of, I'm imagining, 6 partitions had been calculated and were in memory, and it was still in process of finishing up its task. Okay, like you can keep an eye on that, well, where the job is going to run for long enough that that you can kind of poke around in the web front end. So you can do this where you need to, right? If you do this where you don't need to, like if I have you come away with this with the idea that it's just, oh, .cache makes go faster, this is dumb. This is dumb code. If you write it, what you're doing is saying, hey, actually materialize this data frame that doesn't really need to be materialized, put it in memory, waste memory. I'm not actually going to use that thing again. It only gets used there. So that makes my code slower. This one, where I actually do use the data frame twice, probably is going to make my code faster, because I don't have to redo, I guess, whatever calculations hiding in those parens. One of the reasons that like you shouldn't like excessively cache or whatever else you're doing is the execution plan in Spark is, I guess, the subject of some analysis. It's going to get optimized. Spark is pretty good at turning, I don't know, I was going to say dumb code, but not necessarily, just sort of like very expressive code into a good execution plan. It's the same kind of thing that happens on an optimizing compiler. It's the same thing that happens in a SQL query optimizer. It's very much like what happens in a SQL query optimizer. Like in this one, where I've done, okay, have some data, do the things, do some other things, and then keep only the things where that is even. Oh, sorry, keep only the things where that column ended up being 0, whatever that column is, and do some other calculations. What ends up happening here, generate the data, then do the filter. So even though I expressed the filter down here as step like 3, it gets done as step 1. And then all of the things that were basically selects, right? So select to create this column, select to create that column, effectively select, right? With column is just a fancy way to say select star comma. All of those 3 things turned into a single project operation because, yeah, there's no reason to. There's no reason to sweep through the data just to calculate this, just so you can sweep through the data again to calculate that. You should just go through the data, produce all your results, and be done. That's great, right? I can be expressive. I probably should choose better variable names than this, but I can express my calculation in a nice, readable, understandable way, and let the tool figure out how to actually implement that well, as long as I'm not too stupid about it. In this code where I have done, like, I'm thinking about this data set that has these 3 columns in it. 2 of them have to be calculated from the inputs. But then if I do this, just how many rows are there with each unique value for ID? Well, I don't need to calculate the sine of anything or the square root of anything to get this result. And you can see down here in the execution plan, Spark is well aware. It knows that we don't have to calculate the sine or the square root of anything. So even though the calculation is in this data frame, the optimizer figures out, okay, yeah, we'll just sort of proactively drop those columns effectively. Don't bother calculating them. We don't need them. Now, if I had more code that continued on down here that did use them for something, or, if I add another aggregation to this or something like that, then yeah, sure, they will get calculated. But as I've written it, if I was going to calculate df2, don't need those, so don't bother. The reason for this is this is a high level description in the same way that I guess in pandas, you give a pretty high level description, right? You say, hey, I have this data. I want to do this and this and this with it. And pandas doesn't do this because it doesn't lazy evaluate. So it never has the chance to sort of look at multiple steps of the calculation and figure out how they can be implemented best. Spark's pretty good. Again, lazy evaluation is what allows this to happen because Spark can look at the entire history, the entire sort of plan here to do all of this and say, oh, wait, let's put this here. Let's not do that step. That will get the same result. Yeah, when you read something like the Reddit data that you've used, I think by now, either have used or will use this week. Okay, it's not 1,000 columns, but there's a whole bunch of columns in there that mostly you don't care about. And Spark is happy to just skip by them as it's reading your data into memory because you never use them. It's capable, I guess, of basically pushing that like a select operation all the way back to the file read. And you do see that, I don't have a file read explained here. But when you look, you will see it will say something like read CSV and then have a list of columns. And what you're sort of seeing there is those columns and not the other ones. So feel free, throw away those columns. We don't care about them. Only read subreddit and author or whatever, score, whatever we're carrying out in the assignment. So another way to sort of, I guess, express the execution plan is this directed acyclic graph, which I guess maybe like this kind of thing, right? Like if this is useful to you, if it helps for you to think of an execution plan with this kind of picture, great. You will see the term DAG thrown around in Spark documentation here and there. So, okay, I haven't used the word join around Spark yet, but I think you can guess. But I could do it, right? I could have this kind of thing where I read all of these, and this kind of thing where I do all these, and then I have some common column where I can join, and then I'm going to do this. Maybe one of the reasons I might want to look at my world this way is this thing where I take this data frame that's sort of represented by this node, and I'm going to do this with it, then I'm going to do that with it. Well, that's exactly the sort of, if I ever see that shape, That's where I should have cached. I should have said select whatever dot cache, then do all the thing, store it in memory, and then do whatever with it, and then do the other thing with it. Probably that'll be faster. Probably want that. You can end up, by the way, in the situation where caching is the sort of conceptually right thing to do, but you don't have that much memory because the data set is too big. That's probably an advanced version of that. You will see in the web front end, I don't know if I have any, do I have any example here where the calculation is big enough to make this interesting? Maybe. Okay. So sorry, the thing that's gonna bug me here is, well, as soon as the program finishes, the web front end goes away. So I'm just gonna do that. Just add I have to press return. Before it's done, just so I have a moment to look at the web interface. What was I doing? Was I just like talking and typing last week at the same time, and now I've been dumb? Oh yeah, because of course. What are you sorting by? That is not. Okay, so now as this is running, the web front end is sitting here on port 4040 on localhost, and I guess, well, whatever, I can hear my fans ramping up, so stuff is happening. So right now I have 24 executor threads doing stuff that are doing whatever the heck's going on in that code. I have nothing cached. How big a number did I put here? Have I been dumb? Oh, yes, I have. What's a big number? That. Okay. Right. I was doing the example of lazy evaluation at the end of last week's lecture. This is what I get for just grabbing random code. Now, was that too big a number too? What am I doing? Why am I doing a big? I don't need a big number here. Okay. All right. Oh, more interesting, actually. It's a good moment to catch it. So what has happened here down in the completed stages, again, I don't know what this calculation is doing, but like these two like fragments of my calculation have been completed. This one was on the way and actually being executed. And then this one was still waiting. Like this had to be done before the end, but it wasn't started yet. And then I assume so my calculation's done. So now if I reload, all these have been done. Oh, this got skipped. Like whatever this was got skipped. I wonder what it is. And I guess the reason I opened this up is I wanted to sort of point out this SQL/data frame tab with a fraction of the DAG. So yeah, broken into parts, because Spark doesn't calculate the entire program all at once. Of course, it does whatever, well, job or stage at a time, terms that I'm not terribly concerned about for you, but you get a lot of diagnostics here for one, and you also get this visualization. So what's happening here? Well, if I mouse over, I see I'm doing the like mod whatever, the length whatever, and the sign of whatever here. This thing took 21 seconds to complete, and then there was some sort of shuffle operation, which is what the word exchange gives away. What do we? Okay, just colored orange now. Why not? Okay. So 10 million things. Again, I get a lot of diagnostics here potentially on where my performance went. You know, how much data do I expect to have shuffled there? Am I happy or sad about it? It took 1.7 seconds to do it. Again, am I happy or sad about that? Sure. So shuffle read, and then presumably this is finish the sorting that I asked for, and then write the files. You know, how many records made it through here? Is that what I expect? Did I expect most of my data to be gone and there to be a very small number of records there? Do I expect am I happy about the time it took or whatever. You can also see basically a different view of the execution plan here. In the same way, read from the bottom up, but this was, so this. Oh, have we changed we've changed the execution plan, the way a sort is described from what was in my slides, but I'm sure not the fundamental performance or algorithm. So yeah, like again, if this is useful, maybe as a diagnostic tool, unrelated to this directed acyclic graph story, or if you want to think about your world this way, fine. If you see it in the docs, don't be scared. So one of the methods, one of the things you can do in a data frame is you can say, data frame 1 dot join data frame 2, and you can say how. So this, I guess, in pandas, you express this probably with the verb or with the method merge. As a SQL developer, database person, you would call it a join as well. So this is like in their code, I have 2 data frames, both of which have a column name, and I want to join where the names are equal on either side. I want to get those things together. Okay. Maybe this example is a little better. I have something like, I'm imagining something like, oh, we're in GitHub or whatever, right? We have a bunch of data about like what programming languages there are and like descriptions of them and whatever. And then for each repo or line of code, whatever, this 0 corresponds to this 0, right? So this 3 corresponds to this this row is about the R programming language or implemented in R or whatever. So the join is basically, I want to get that together, right? I want an R here, and I want, like, on these 2 rows that have ID equals 2, I want the word Python to appear beside it. That's the join operation. You can express a join condition in a couple different ways. You can give this Boolean expression. My advice is that you don't, because if you express your join condition this way, you get a duplicate of the column ID, because this like Boolean condition, but Spark doesn't inherently know that there's going to be 2 things called ID and they're actually going to have exactly the same values in them. And that's really annoying. Like, then dropping one of them sucks. This is way better. If you just say join on this column. So you have to have the column have the same name on either side, but you could probably arrange the world that way. This is a way better expression, and you get a nicer output for it. Okay, I got, beside the word ID, ID equals 2, I got the word Python. Okay, I joined. But in a big data world, if you're on a compute cluster, joining is maybe kind of expensive, because, well, again, I might have the row that says ID equals 2 means Python might be over here, and then I have all the data over there, or it's like some of the data here, some of the data there. So I've got a lot of stuff to move across the network, basically everything, right? Kind of depending how I'm going to do this, I've got 2 sides of my join, and I need to get, I mean, obviously I have a small example that fits on a slide, but I need all the things with ID equals 2 from both tables to get together so I can actually produce those rows. That's maybe a lot. That's maybe more than I want to move around. It's a shuffle operation. It's kind of like the worst possible shuffle operation, because I have 2 tables that need to be shuffled in order to get the things where they need to be. But, well, think about all the times you've ever joined tables in a SQL database, and if that's never, sure. But, well, come on. My tables here, like the list of all programming languages or whatever I'm imagining this table to be, that's not big. How big could it be? Hundreds of rows or something? This data is probably big, right? Again, whatever's going on here, every day, every project, every whatever, this could be a huge data set. So what I have, and this is very often going to be the case in a join, think about the joins you've made, where you have a big side and a small side, So this is still, one side of the join is small, 4 rows, 40 rows, 400 rows, 4,000 rows. Those are all small. Joining to a big data set, totally possible. Well, why? Like if I'm going to tell the story, and if both sides of the join are big, I have to tell this whole complicated story. But if it's not true, if I don't think one side of my join is big, I'm basically going to treat it like this, right? Like effectively what's going to happen is, well, every time I see 2, I want the word Python beside it. This is a very small data set. Well, what I can do is, if it's small, I can make copies of it. Broadcast is the verb here. So take this one side of the join, the small side of my join, copy it. It's like send every executor this copy of the join, and then this is really easy. If everybody has a copy of this data set, then joining to this data set, even if it's trillions of rows, no big deal. Just look up in the data. What's 2? Python. What's 3? R. And all of a sudden, that story I told is not a shuffle operation, at least not with respect to the bigger data set. And that should be a lot faster, right? I don't have to move the big data set around. I get embarrassingly parallel, and I'm very happy. So the term here is broadcast join. It's not unique to Spark, but it sort of makes sense in this context of like I have distributed data, and I have one side of my join is small enough that I can send copies of it, broadcast it. But if that's true, all of a sudden a join is not expensive anymore. So Spark gives you a way to hint for this, and say, hey, Spark, I think this data is going to be pretty small. I want you to make copies of it if I say to join it. So that might be nice. And again, the way you spell it is something like this, just on that data frame, the one that you know to be small. If you get this wrong, and I've seen students do it, if you try to broadcast the big side of your join, what you're about to do is wait a long time to run out of memory. Because if you have a big data set and you say .hint broadcast and try to join it, well, send a copy of it to every executor. Well, and you just wait quietly while all your executors run out of memory and fail. But if you get it right, the result is the same, right? Like I'm sort of logically correct either way, but what I'm going to get is a lot better performance here. And I see. So in the version without any hinting, the plan is basically treat each side of the join the same. Hash partitioning on ID. So yeah, this is probably like take the ID column, run it through some hash function, and then depending on the results and like everything that hashes to 0 there, everything that hashes to 1 there, or whatever. Okay, but then everything with the same ID value would be together, and you could kind of finish the sort merge join. Fine, sure, great. Or if I give the hint, there is a broadcast exchange. I assume this is on the small side of things. Yeah, broadcast the small side and then join to the big side. That should be cheaper if everything in my story holds true. It will be if you're in this scenario. I believe this week's exercise you have to do this, or next week at the very least. I imagine, unless something has radically changed in Spark, that's what you'll see. It's still expensive to do a join if you have 2 big things to join together, but Spark is pretty good at its job. The optimizer is pretty good at its job. One thing I will point out actually that adds some complication to the exercise is I live in constant fear of new Spark versions because the optimizer keeps stealing from me. Like I have an example, right, of like, oh, look, if you don't broadcast join, it's slow. And if you do broadcast join, it's fast. And then at some point they added like some automatic detection that when I say this is a plan, it's just a plan. What happens is it starts doing a full sort merge join, sort of implied here, but then it can at some point think, hey, wait a minute, these do not seem like they're the same size. It seems like this side of the join is actually going to be pretty cheap. I'm going to switch to a broadcast join. So that takes a little while. Like this is going to be slower because it takes a while for it to sort out that it should have done a broadcast join. It's still worth it for you to give the hint. In the exercise, I've had you like explicitly turn off that very helpful feature so you can see it. Because I think it's still worth being a good programmer, even if the tool can kind of save you from yourself if you're not. Anyway. Okay, where were we here? That was that, right? Yep. Okay. So these are the kinds of things Spark can do. Let's talk about how to sort of use it effectively. Actually get stuff done. I guess that's the theme of this slide deck. One thing I just want to point out here, like, why are we scared of shuffling? And well, we're scared of shuffling because of kind of this number, that you can only move data so quickly over a network, depending on your network, obviously, but there's still some speed limit. And it's certainly going to be slower than getting your data out of memory. If I'm about to do a broadcast join, I can get almost everything except the small side of my join dealt with as a pipeline operation. It will be on the local system one way or another. I can access it quickly. If I have to shuffle it, I'm down on this line of the table moving stuff across the network, and I'm going to be sad. This little aside, and this is a Julia Evans too, isn't it? My God, I love Julia Evans. Everything she does is awesome. Anyway, so this game is, arguably unrelated to what I'm talking about, but it's basically, you look at this and you say, okay, I have a time budget of 1 second. How big can the number be? How many times can this loop execute on a reasonably modern computer in 1 second? Plus 1. It's a big number. Like that's a really, really fast little loop. And the right answer is the number on either side of the right answer, right? So whichever like power of 10 is less, like 1 less, 1 greater kind of thing. And then doing the exact kind, or the same kind of thing in Python. How much slower is it? A couple orders of magnitude? Less than I would have thought. 8 times slower or something. Anyway, the reason I'm here is, well, one, because this is fun. But like, how many times can you download google.com in 1 second? 4. And of course this has an implication, right? Like, it's all well and good to say you can do a loop in Python 6 to 8 million times per second. Well, it depends on the loop, doesn't it? This loop, you can only do 4 times a second. How slow is writing to disk really? How many, what is this? Strings? Chunks? How many 1 million character chunks can you write to a disk in a second? On probably an SSD? What did I say? Million character chunks. 1 second. Shut up, really? Huh. Oh, it's in bytes. Sorry. I shouldn't be scoring. My score was not the number of chunks I can. Okay, so whatever I said times a million? Yeah, whatever I said times a million. Perfect. Anyway, I think you should have some sense of this. This is a good game, but not quite the point. The point for us is real computers are stuck in the way when we're trying to do big data. If I have a terabyte data frame and I want to just say .sort, it's legal, right? It's not a syntax error. So I can guess. Like I can make a guess at least of how long, if I have 1 gig Ethernet, which hopefully I would have 10 gig Ethernet in a modern data center, but okay. I might also have more than a terabyte of data too. 2 hours. Okay, like I'm willing to wait that long, maybe, to sort my data. I then probably have to do something else with it, sort it to disk or send it to disk or something like that. But this is definitely not something I can just do Like I can't write dot sort on this data frame without thinking about it. How about that? If I want to join, I have to think about it. The TerraSort benchmark, this is certainly not the status quo. This is like 10 years old or something, more than 10 now. It's shocking how fast you can sort 100 terabytes worth of data. And the Spark record here, this is like consumer, like you can get this. This is AWS nodes. There's no special like custom hardware or like private data center, anything here, which I think the current TerraSort records are. Like we can't do that. We can do this. Well, I don't know what your AWS budget is, but with a sufficient AWS budget, any of us can have 100 terabytes worth of data and sort it in 23 minutes. I would have guessed wrong. Like I would have guessed a bigger number than that. But anyway, okay. On to the meat of it here. This is so we've been doing this all the way, and I keep typing these things, and I sort of hear myself almost say column expression, but that's what all of these have been. All of these things where we're expressing like what value goes here or what values go in this column to Spark, all of those are column expressions. They are column objects in Python. So if I just look at this and ask for its type, it will be a column object. So will this, so will this, so will this. All of these are, they're having the same job. And of course, it looks different if I just refer to an existing column versus do some calculation on it, but they're all just column objects. I can put them all in a select operation. If it's a column object that has type bool, like that returns true or false, I can put it there. I can group by, like, if I want, where'd my code go? Oh, this. Like I can group by column 1 times column 2 if I want. That's totally fine. I can put any column object I want in there. Usually I would just put the name of a column. Like I would just refer to one column there, but I don't have to. And again, I can group by a bunch of different things too. So these kinds of things are that, right? I can say like the power operator, or like I can say +1, I can say times, like all of those things are just going to work on column objects. Column objects have some methods that are kind of useful, like dot not null. As type, sure. For a type conversion, why not? Okay, so there's a few things in here. Anyway, I think something like dot is not null. Fine. Good spot for it. But the problem is, I think what happened is as Spark was growing in its like initial creation, they started to realize like, there's going to be way too much here. Like there's so many methods, like so many things you could do with a chunk of data in like a data frame tool like this. Boy, maybe I don't want everything in the same namespace. So at some point, I think they basically just started saying, okay, no more methods there. Now it's functions that will take a data frame column as an argument. So those column functions are why we've been importing functions, like in the template that I've given you. There's a bunch of stuff here. I don't know if I scroll randomly. Sure, why not, right? I can calculate the SHA-256 of a string. Sure, right, great. Like maybe that's the thing you want to do. And if it is, good to know, right? You can take, so this is functions dot, oh yeah, they've imported it, weird. Okay, functions dot this, give me the 256-bit version of this hash. Great, fine. You're right, dot show, sure. Okay, great, good to know, right? It's nice to know I can do that if I want. There is a lot of like useful and expressive stuff in there. So this is, oh right, so this is just like a printf style formatting, or well, I guess sprintf, where you get the result back. Yeah, okay, I want to take a number and a label and I want to turn them into that. Yeah, I guess this is something, whenever you had to do this, the like year-month date, that when you were doing a pivot for whatever reason, okay, you could do that kind of thing if you want. a couple of things turned into a string, or how long will the string be, or how many days in between this date and that date. Okay, great, right? There is a category here that's worth, I think, mentioning. Like, most of these categories are just, you're doing different stuff with them, different kinds of calculation, but I guess that's why I put the link there. The aggregation functions have this different role, which is, I just did a group by, now what? And again, remember, a group by does not produce data. A group by followed by an aggregate, that produces data. So almost certainly these column functions I'm going to put inside the .ag method. And I would like to, okay, average, right? This is one we can all imagine. Group by this. So put all of the things for, the same ID value or the same client or whatever together, and then average the monthly spend, whatever you're doing. Great. There's some consistency. It's gotten a little better with the versions of Spark. They're trying to obviously make things better, but like, in the column object, there's a method like dot between where I can say, less than, greater than kind of thing. I could also just say less than and greater than. Why would I prefer one over the other? I don't know. Why does this one get to be a method? Probably because they thought of it first. And I can say, if I want to know, is the first character this, I could spell it this way, or I could call the substring and ask if it's equal to that. Why? I don't know. Again, it just is, right? It's a historical weirdness, and we live with it. Just keep an eye out. Like, there's sort of these two places that like logic can hide. But yeah, it's annoying. And again, they've gotten better. At least they've gotten better with the naming. So approx count distinct is, I think, now the only way to spell this. They have gotten rid of the Java style spelling of the method. Those are gone, at least. So when I say approx count distinct, maybe you haven't thought to ask how it gets calculated. It turns out not the way you probably thought if you haven't thought about it. Because of course we're writing Python code. So it seems totally reasonable that if I say approx count distinct, or if I say SHA 256, or I say timestamp microseconds or whatever, it seems totally reasonable that there might be some Python code there. And there really isn't. All we're doing, like effectively in Python code, is building execution plans. So in the Python code that I write, that is the driver process, I get to say, I want to calculate the SHA2 of that, and I want to figure out how many milliseconds are in this timestamp, please. And then that execution plan gets handed off to the Scala engine, which is Scala code, which is compiled to Java bytecode, and it's run on a Java virtual machine, which is why I'm like fighting with the Java virtual machine version on my computer here, because the code that they have, the nice Spark people have given me, has some incompatibility, and I'm sure a release from now they'll fix that up, but we're in this moment in history. So even though I'm writing Python code, my work is being done in the JVM. So, okay, that means a couple things. One of them is it kind of doesn't matter what language I write. Where's my... Like, there's a Python Spark API. Like, I can write Python to produce this execution plan, I guess. I can write Java code to produce an execution plan. I can write R code to produce an execution plan. It's the same plan. So it all works the same way with the same Spark query optimizer and everything else. We're writing Python because, well, we're used to it, because I think by far most of the Spark code that gets written is written in Python. I think it's the right tool. But there's also a few other things out there. Like the dataset API that like I've not really used in any serious way because it's not accessible in Python. And the reason it's not accessible in Python is it's strictly typed, statically typed. It's statically typed. So like the language has to know what the types of all the results are in order to build that execution plan. And that's just not known in Python in general. So it just doesn't fit. So probably this is a good thing. Like probably this whole story is good because on average, mostly as long as everything is normal, code done on the Java virtual machine is going to be faster than in the Python virtual machine where you run things. It's just nature of the language. Again, the static typing, so everything can be planned a little better. Great. It also means I could, like if I just have a bunch of R data and I want to switch to Spark, it's probably not that hard. But like I already said a week ago or two, like if you do something that goes wrong in Spark, it's really hard to debug because, and this is yet another layer on that, because I write some code and I think I'm writing Python code and then I run it on the cluster gateway. But what actually happens is some Java logic, and then that Java logic gets sent out to a different computer. And if then an exception is thrown, boy, like what hope do I have of getting any kind of useful traceback? So this is why, oh, and also, God, I get this all the time too. I will have students come to me and say, there's some problem with the cluster. And I'll say, okay, what makes you think that? I can't write files. There's something wrong with the disks on the cluster. And I look at their code. It's like, no, you are getting, like, to be fair, like you will get the exception on the line of code where you say data frame.write. And that would obviously make you think that the error is about writing files. But the actual cause of the error could be 20 lines up and that code just didn't execute yet. It wasn't until the execution plan had to get evaluated that anything happened, and that's why your error is shown on the .write line, because that's when it starts doing the execution and actually materializing the data. Also, it happened on a different computer in a language that you never wrote. It's rough. Something else that is sort of implied by that is that user-defined functions are possible. And this is just like, I want to write a Python function and I want to call a Python function. Well, an implication of this is that, well, if I write a Python function, my code has to be handed a Python object. There's no Python objects in the story before that slide. So Spark gives me the option to do effectively a dot apply. Like it would be called dot apply in pandas. And that's for each row, call this Python function. Okay. That means the Python, like the arguments have to be constructed as Python objects. I return a Python object that has to be somehow converted back into something that can be put into a data frame. That sounds like it's going to be expensive, but I guess let's take a break before we talk about it. And yeah, see you in a few minutes.